Okay. Any questions? You guys have any questions on anything? All right. Today we're starting a new topic, which is regression. Okay. So regression is what we're going to do today, and it's related to what we've done before, which is correlation coefficient. Remember what we calculated the correlation coefficient for? That was R. That was the number between 1 and -1. And what does that correlation tell you, that correlation coefficient? And when would you want to calculate a correlation coefficient? What type of data do you have when you calculate a correlation coefficient? What type of data are we talking about? Is it categorical data, ordinal data, continuous data? What type of data are we using when we talk about correlations? Anyone?
We have a bunch of data points.
Okay.
So,
yeah. So the outcome variable has to be a continuous variable. So the y variable is continuous, and the x variable is also continuous. Okay. So when your x variable is continuous and your y variable is continuous, then you calculated a number called the correlation coefficient, which tells you how strong the association is. Now, that correlation can either be positive, 0, or negative, and depending on what the sign of that correlation is, it tells you how those two variables relate to each other. Remember that? When we talk about height and weight, that would be an example of what type of correlation if I'm looking at a study of height and weight. Would that be positive or negative? Yep, that's an example of a positive correlation, okay? So if I wanted to look at maybe like the SAT scores and first year college GPA, that would be another example of a positive correlation. And one of the questions that you might want to ask is, like, well, what type of variables should we use? What type of X variables? And which ones have a stronger correlation? What do you guys think? Do you think your high school GPA is more related with your first year college GPA or the SAT? So they've been talking about getting rid of the SAT. Maybe the high school GPA is a better predictor. Maybe the SAT is a better predictor. Which one do you think it is? So we will be able to address those questions with the correlation coefficient. We could also put both of those variables together. I could also, I could use your high school GPA and your SAT scores together in order to predict one's first year college GPA. Okay. So we'll talk about those sort of things in regression, okay, which is the point of today. In a regression analysis, you're building a line equation that tries to predict y from x, and both your y variable and x variable are they're both continuous. Okay, so we're going to begin with the example that your professor went over, put together for you. And we're going to study Dungeness crabs, which is Cancer magister, which is also known as Dungeness crab. So we're going to look at a study looking at two variables of Dungeness crabs in order to predict the age of these crabs. Okay, so to give you some background information on this. From the reader, they tell you that they usually only, when they fish, they fish mainly just male crabs, because what they don't want is they don't want to fish the female crabs until they're old enough, because they populate. They were able to populate the rest of the crabs. So they want to mainly just fish the male crabs, and they also put a limit on the number of them caught. So, as an example, from 1947 all the way to 2006, these are the millions of pounds of crabs caught over the years, and this is along our coastline. And they thought about possibly lifting the restrictions on so that you could fish both male crabs and female crabs. And whether that would affect the population or not. In fact, if you look at the reader, I believe they said in Canada, they actually allow for fishing both male crabs and female crabs. But the reason why, the reason why they fish mainly just the male crabs is because they want the females to have an opportunity to produce offspring for a few years before they are fished. So that we need to be able to predict how old a female crab is, and they predict that by the size of the crab. And how can you do that? How can we use the size of the crab to tell how old she is? And part of it is some problems because the crabs have an exoskeleton. So you need to be able to use the size of that exoskeleton in order to estimate the age of the crab. Okay, some more information. Crabs, they molt they go through molting cycles. And here's an example where you can see that an example where the crab is molten, and so what you'll see is there's going to be a pre-molt size and a post-molt size in terms of the size of the carapace. Okay, so females molt mainly in April and May, and that coincides with the mating season. And during that time, both the female crabs and the male crabs enter the shallow water. And the females embrace prior to molting. And in their reproduction cycle, the males deposit sperms when her shell is cast off. And once the female's new shell hardens, then they separate. And the female carries a sperm for months while the eggs develop. She both lays and fertilizes the eggs, and then she carries the eggs until hatch. And here's an example to tell you how big the larval form is. It's only 1 millimeter, it's fairly small. This is against a dime, so you can see how small that really is. And usually when the crabs are first born, they try to stay away from the adult crabs because there's cannibalism. So what happens is they molt many times as they mature. And the way that they molt is they absorb water and they split the shell and they kind of back out of the old shell and as they grow, and then they expel the water, and then there's more room for them to grow. Okay? So this is the process where they go through, and every time every time they molt, the next size should get larger. And one of the things that we should be able to do is when you look at the post-molt size, we want to be able to know how can we predict the size of the crab beforehand. Okay? So that's the question that we're trying to address. Given the crab's post-molt carapace size, estimate how big it was before it. Okay? So that's the problem. Okay. There's actually two ways that they've done this. Okay, if you look at the reader, there's two ways that they've done this in order to figure out how large they grow in each molting season. On your homework assignment, do you remember that recapture problem? That was your homework assignment. When's that homework assignment due? Is that due Friday? Okay. Well, on your homework assignment, there was a question where they asked you to. You could do it several ways, but the best way to do that, one of that question, I believe is number 6, is by a hypergeometric. So do you remember that question that we did in terms of the Salk vaccine? Okay, that's a problem where you look at two different groups and you want to figure out the p-value, and the way you want to approach that is using a hypergeometric distribution. In relationship to this, you could also when you look at those types of problems, what we do is we have this thing called capture-recapture. So we capture a whole bunch of crabs and we tag them. They each get us maybe like a serial number, and we know how big they are. Okay, and then we release these crabs, and then we capture them again, maybe a couple months later. Not every single one, but those that we do, we have the serial number, and we're able to figure out how large it has grown. Okay. So that is that first method. So before the molting season, they tag so many crabs, 12,000 crabs, and they're not going to capture all 12,000 again because some of them probably die or some of them get eaten up. But those that they can get back, they're able to see how much difference of a size that they get after the molting season. So that's called that capture recapture method. There's also a second method, which is when the crabs were caught in a mating embrace, they measure the females before and after molting, and then they release it. And the data that we're going to look at is based mainly on the first method. Okay? But there were two ways that they actually collected this data. And the data that we're going to look at shortly will be based mainly on the first one. Okay, so the carapace of the crab, they try to measure that width right there. Okay, so they look at the largest width that takes on, and that would be like the, so when they get it, that would be like maybe the post-molt, and then they have to try to figure out what happened, how big was it beforehand. That's what they're trying to predict. They're trying to predict the season before. All right, so here's the data. So even though we saw 12,000 crabs before, they were able to collect only 400. They were able to recapture 472 crabs. And the data that they have is the pre-molt size, the post-molt size, and therefore they're able to calculate the increment. So they could go post minus a pre, which would be the size. And then they also know which year that it was captured. Okay? The way that they got all these crabs was that they went out there and captured them. They also pay fishermen if they did they were able to catch these crabs. There's a tag on it, and if they turn it in, they get it's like a lottery. They awarded like a $500 lottery at the end of the season as a way to encourage the fishermen out there to turn in these crabs when they encounter them. Okay. So these are all the things that they did in order to try to collect these crabs again. And so they got a total of 472 when they were done. Okay. Let's look at these two graphs. So this is the pre-molt distribution, and that's the post-molt distribution. Okay. So here's pre, and here's post. And notice that as I switch from one graph to another, we're keeping the x-axis the same. So what is the difference between the pre and the post? What is the main difference? Yeah, I mean, like the distribution looks almost the same, but which has a larger average? The post, as you would expect. So after one molting season, you would expect the size to get bigger of these crabs. Okay, so what we want is we have the pre, and then we have the post, and then we're just looking at the density of it. And we notice that the post is they're larger after a particular molting season. And what we want to be able to do is if I have a crab at where I have the post-molt size, I want to be able to predict the pre-molt size using this technique called regression. Okay, so here's a plot. So this is the post-molt size, and this is the pre-post-molt size, pre-molt, and the correlation is definitely positive. In fact, this is a very tight correlation. So we're able to predict this fairly well. Most of the data is above 120, so I could calculate the correlation of this whole thing, or I could just cut it off at a 120. So maybe what we're going to do is just look at a subset of these crabs. So we're going to exclude everything under 120 millimeters. So everything from 120 and below, like all these things, those could be seen as outliers. We're going to exclude all these ones below and just look at those crabs that are above 120. So that's what this graph looks like. And when you exclude all the crabs under 120, and now we look at this part of the graph, this correlation is 0.98, which is very, very. The correlation is between 1 and -1. So this tells you that you're able to explain 98% of the variation based on the post-molt size. Okay, why 98 is because if I know the crab is at maybe like 140, there's still some variability. I cannot predict it 100%, but 98% of the variability I can predict using the post-molt size of the crab. It's not completely perfect. If it were perfect, all the points would be what? If the R is equal to 1, what type of, actually this is R is 0.98, so I said this wrong. R is equal to 0.98. So the percentage that I'm able to explain is actually 0.98 square. So 0.98 square is the proportion that I'm able to explain. Now, when you look at let's say 140, you can see there is some variability in the pre-molt size. So even at crabs that were all at 140, they didn't all have the same pre-molt size. And because of that, that's why you don't have a perfect correlation. Okay? If you have a perfect correlation, which means a correlation of 1, what would that imply about all the points? Yeah, straight line. All the points would be linear. You'll be able to predict everything 100%. Okay, and as Dr. Nolan was saying, how good of an association, how strong an association do you expect? Really depends on the discipline. If you're talking about physics, you could probably expect correlations about this high, but most social sciences, a correlation of 0.6 would be very strong already. Okay, so how strong of a correlation is really depends on the application and the field. Okay, but so correlation we talked about before, but it's not just the correlation we want. We also want a line equation. We want to be able to draw a line equation through those points. This is called a scatter diagram. And the reason why we want to draw a line equation is that way, if I know what x is, I can predict y. Okay? So I can just plug it into that line. And this looks fairly linear. Okay? So those are some of the assumptions that I have to make. And looking at this graph, it looks fairly linear. So I'm going to draw a straight line through this. Eventually, I'm going to draw a straight line through this and be able to predict y. But before I do that, I'm going to cut it off into different sections. I'm going to examine different strips. Maybe I'm going to examine it at 130, 135, 140, 145, 150. And I'm going to look at the averages within each group. So here's what I mean by that. Okay, so here, this is the pre-molt distribution for a given post-molt size to the nearest 5 millimeter. Okay, so let me go back to the last graph. So if I want to look at everything that's at 125, which means I'm looking at everything that's between 122.5 to 127.5, and that would be the post-molt size. So when I'm looking at that very first diagram, in a 125 millimeter, that is the post-molt size. So when the post-molt is 125 millimeter, that is the distribution of the pre-molt. Likewise, here is all the crabs where if you look at this diagram, where the post-molt is 160, and there's some variability as well. Okay, so within each one there is some variability. How are these graphs created? Okay, so let's try to estimate a pre-molt size of a crab that has molted, and its carapace measure 135 millimeter. Okay. So if I were to look at it here, 135. So what I would do is I would look at maybe all the crabs between 132.5 to 137.5, and then I would calculate the average y value, which is the average pre-molt. So the average pre-molt of all these values within the strip is 119.4. Okay? And I'm going to do that for every, maybe for every 5 units. I'm going to repeat this. Okay? And when I do that, I get this graph. So here's a graph where every 5 units average, and I get those red dots up there. Now, do those red dots, do they line up in a line? Almost, but not exactly. Okay, they line up fairly well. So if you were to draw, if I were to ask you to draw a line here, it's much easier to draw through those red dots. But there's still, you will not expect them to be perfectly on a line, but they'll be very close if this model works. Okay. So what I'm going to do in the next slide is connect all those segments. Okay. So you can see they fall roughly on a line. So this is one way to get a very rough regression line. It's not quite a line because those are segments that are connected together. So what is the best way to actually draw one straight line through the scatter diagram? So that's the problem that we're trying to address right now. Okay? What would be the best way to draw one line through those scatter diagrams, and what criteria should we use? So we want one slope, one intercept, instead of a whole bunch of segments which are kind of wobbly. Okay? So what would be the best way to go about doing that? Okay, that's the question. And this question's actually been solved in many different classes. They actually solved this in the same problem you will encounter in Math 16b. They actually teach it in that course. They teach it in Stat 2, obviously in Stat 20 right now. And also in Math 54, the linear algebra course. And every time they teach this, it's almost unrecognizable between these different methods. But they teach the same problem for each one of those. And this is called the regression line, which essentially find the line that best describes this data pattern. Okay? And the way that the criteria that we're going to use is this one. Okay? So we're gonna use a calculus way to describe this. We're going to try to minimize the sum of the deviation square. That's what we're trying to do. Okay? The deviation is how far an actual data point, which is the pre-mode, is away from the from A minus B times post-mode. So you think about the A minus B times the post-mode as the predicted value. So we're trying to minimize the actual value from the predicted value. And if I can minimize those deviations square, that's how I'm going to find my best A and best B. Okay? So I'm going to go through the derivation of this formula more formally at the very end using partial derivatives. I could have also done it using linear algebra, but partial derivatives is the way I'm going to go. But the best way for you to think about this is that you're trying to minimize those distance square. Okay? The sum of the square deviations. Okay, so more formally, this is what Dr. Nolan wrote. She said, so you can think of y as the value that you're trying to predict. X is the value that you're given, which is the what? X is the post-mode. And we're trying to predict the pre-mode size. A is the what? A and B are the line equation, are the parameters of your line equation. So A is the intercept of the line equation, and B is the slope of the line equation. So when you write A plus BX, that's your line equation. Okay. The reason why you see those minuses is because we're taking y minus the predicted value. So that is in more formal language. Okay. Now, what's nice is that the computer does this completely for you. Okay. I'll talk about how to do the calculations in a moment. But when you're using R completely does this for you. So the way that we're going to set this up is we're going to say we have this data set. So we're going to subset it. So we're looking at we're looking at only the post size greater than 120. And then we're going to use this function LM, which stands for linear model. Okay. So when you run this command, crab LM, we're going to call it crab LM, equals LM, which stands for linear model. And that is a function. So that tells you the pre-size is a function of the post size, and the data is crab's S, which is our subset. Okay. So by running that LM function, what we've done is we create a whole bunch of vectors and a whole bunch of data frames. So I think either vectors or data frame. But one of the linear models that you see is once you run that model, you could go type names and then see what things are created. One of the things that are created will be the coefficients. So if you type crab LM $coefficients, you'll see that intercept minus 29.18 and 1.10. And that tells you that's your A. A is minus 29.18, and B is 1.10. So it does that for you automatically. So 1.1 is your slope, which is B, and the intercept A is minus 29. Now we're going to add this line equation into the plot to see how it looks. Okay, there it is. So the blue line is the regression line. And what do you notice about the blue line and those red segments? They're pretty close, right? So we could have used those red segments to kind of estimate where that regression line is, but it's much better to have this one line equation. And that tells me if I have to interpret this 1.1, what are the units of B? This is a slope, so what are those units anyway? What do you think that 1.1 stands for? And what are the units of that 1.1? If it's a slope, it's got to be what? Change of y, units of y over units of x. Okay. What are these units right now? These units are in what right now? They are in millimeters. Okay, and they're both in millimeters right now. They don't have. I mean, they actually didn't have to have the same units, but these are the same units right now. I mean, if I were measuring people's height and weight, height could be in inches and weight could be in kilograms. So these things could actually be in different units. In this case, they are the same units. So that 1.1 is really that tells you that for every 1 unit increase, in what? For every 1 unit increase in the post-mode size, there's an associated increase of 1.1 in the pre-mode size. Okay. So for example, if I took this, if I saw some that's 130, and I saw another one that's 140, this one I would predict to have a larger pre-mode size. How much larger? How much larger would I predict something at between 130 to 140? Well, from here to here is how much across? That's 10 across. And the slope is what again? 1.1. And so what's 10 times 1.1? 10 times 1.1 is 11. So to go from 130 to 140, I expect a difference of 11. Okay? So that's why, so it's a way to tell you that, look, for every 1 unit increase in the post-mode size, there's an associated increase of 1.1 in the pre-mode. Okay, so that's called the regression line. And I haven't told you how that was calculated yet. So let's go ahead and compare the regression line. So I'm going to take off all those data points so that you only see the averages. So if I take off all the data points and you see only the red points, which are the averages, you see that the line equation, the regression line, goes through practically all those red points, okay, which are the averages of each strip. Okay, so how do we calculate that line? I know R does it for you automatically, but if you want to know how that line is actually calculated, the regression line, y hat, and that symbol y hat represents the predicted value. Remember, there's y, there's x, those are the actual value, and y hat represents the point on the regression line. That's the predicted value. So if I want to get the predicted value, it's simply a plus b times xi. So if I just plug any of the xi's into that equation, that will give me my predicted value. Okay? How do you calculate that b? Well, another way to calculate b is just r times sd of y over sd of x. Okay? And does that make sense that b and r should have the same sign? Okay? If r is positive, if you have a positive correlation, what do you expect your slope to be? Positive as well. Okay? If your slope is negative, then you expect b to be negative. If the correlation is 0, let's say you have a scatter diagram, which is pretty much like a circle like that, where there's no direction. So therefore b is flat. If b is flat, r is also going to be 0. Okay. So you should see the relationship between the slope and the correlation coefficient. All right, the intercept. The intercept is equal to A is equal to y bar minus bx bar. Okay? Notice I wrote down the formula for B first and then A. It's because if you were to actually have to calculate this by hand, which you don't need to since you have R is going to do all this for you. But this tells you that, that if you calculate B first, then you can get A. And the reason why you can get A using that formula is because the line equation, the regression line equation, always goes through the point of averages. Okay? What is the point of averages? The point of averages is just x bar comma y bar. So in any scatter diagram, like right here, I don't know what the average is, but it's somewhere probably around maybe like 145 is where. Well, this would be the average of those that are above 120. So maybe the average is somewhere around here. There's a point of averages, which is the x bar y bar. Okay. It may not even be an actual data point, but there's a point of averages. And the line equation always goes through that point of averages. So the regression line goes through x bar comma y bar, even if x bar y bar may not be an actual data point. And so that's what the point of averages is. And I just want to remind you what R is. R is the correlation coefficient. Okay? All right. So how do we actually derive these formulas? Okay. So essentially what we want to do is to create a function f where f is equal to y minus a minus bxi. What does that represent again? That's y minus the what? What is a minus b? What is a plus bxi again? Those are the predicted values, right? B is your slope, A is the intercept. So a plus bxi, those are the predicted values. So yi minus that, that's called the deviations. And the deviations could be positive, it could be negative, okay? So, so when you look up there, that first equation, that is what we want to minimize. Now, it's going to seem kind of strange, but now I'm going to call my I'm going to differentiate that function with respect to A and B. So I want you to think about A and B as your variables. Why do you think of A and B as your variables right now in this calculus problem? Because we're trying to do what? We're trying to find the best what? Best line equation. Best line equation. So there's many line equations I could draw. I could draw different A's, different B's. But I'm trying to say, well, what line equation, what is the best A, what is the best B that I can come up with that would minimize that function? So that's the problem that I'm trying to address. And the way that I'm going to do that is I'm going to take the two partial derivatives. So I calculate df, df dA, df dB, and I get those two equations, using the power rule. And I multiply by -1 because that's using the chain rule. I multiply by that negative xi, again, using the chain rule. And after you calculate the two partial derivatives, what do you do next? When I'm trying to minimize a function? Set it to 0. That's right. So I set the two partials equal to 0. Okay? So now I set the two partials equal to 0. I need to solve for A and B. So let's go to the next slide. All right, so let's derive the intercept A. That's actually not so bad to do. So let's go back to what we have before. All right, so what we have right before is we're down to this equation, y minus a minus bxi equals 0. So let's focus on that equation again. All right, so y minus a minus bxi is 0. Okay. So from the top equation to the next equation, what did I do? I just split up the summation. Okay. So I get sum of yi minus sum of a, and because b is a constant, I could just pull it out of the summation sign, minus b times sum of x. Okay. And then from the second equation to the third equation, I just divide by n. All right? Now, what is sum of y over n equal to? Sum of y over n is equal to what? Average. That's y bar. Okay? sum of x over n is just x bar, so that's bx bar. Now let's look at the middle term. Why is that a? What is the sum of a constant? Sum of a constant is just n times that constant. Okay? So if I write down what sum of, for example, if I write down sum of 10 from I equals to 1 to 3, that means 10 plus 10 plus 10, which is 3 times 10. Okay? So that middle term, sum of a, well, sum of a is just equal to n times a, and n times a divided by n will give me a. So now I have y bar minus a minus bx bar. And then, so now I solve for a, and I get this. Okay? And that just verifies that the equation always goes through the point of averages. Okay? So that's the derivation of the intercept a. All right, next slide. This is the harder one. Now I want to derive b. When I'm finally done, this is the result. Okay? And that may not quite look like r times s d of y over s d of x, but if I play around a little bit, I can get it to look like that as well. But let's start from the beginning. Okay? So where I get that top equation from, let's go back 2 slides. Remember my normal equation? Okay, so now I'm looking at this other part. Okay, so I'm starting with right here. Okay, so I already know what a is. A is equal to y bar minus bx bar. So that's what I replaced it with. And then I combine some of those terms, so that becomes y minus y bar. I factor out one of those b's, I get that. And then I do the same thing, I split up the summation. So I get my third line. Now I'm trying to solve for b, so then therefore b is equal to this over this. And this is perfectly fine. You can leave your answer like this, okay? But most of the time they write it this way instead. And the difference is, instead of writing xi, is xi minus x bar. And instead of xi here, it's xi minus x bar, and therefore that's why it's xi minus x bar squared. So this part is a little bit more difficult to understand why this works from here to here. So if you come into office hours, I'll definitely can explain that. But very briefly, the reason why that works is because the sum of a deviation, the sum of all your deviations is equal to 0. Okay? So I haven't shown you very explicitly why this last line works. But if you come by my office hours, I can go over that more in depth with people. But the main thing is that this is perfectly fine. This is the way it's generally written. And if you work with this a little bit more, you'll get this other formula, which is the one that you're probably more likely want to remember, this one, which is b is simply r times the sd of y over sd of x. Okay? And the main way that they've been calculating these formulas is to minimize the sum of the deviations, sum of the square deviations. Now you'll notice that we only took one x variable to do this problem, and but later on, like if you're doing your projects, if I'm trying to predict y, you may not just have one x variable. You might have an x1, an x2, and x3, and the same strategy holds. Okay, you're still minimizing the sum of the deviation square. Okay. So if you're trying to build a more complicated model for your projects, you're essentially doing the same thing, but instead of one variable, you might have several. The other thing that you might do, instead of regressing on just x, you might want to regress it on the natural log of x. You might regress it on x squared. Those are some of the things that Dr. Nolan talked about when she did the body mass on all the different animals and talked about the surface area. Remember that where there was like an x squared term or x to the some power. So you don't have to have a linear term. It could be x to the some other power. Okay. So when you're working with your actual data, it may not be so simple where you just regress y onto one x variable. You might regress y into maybe like an x1, x2, x3, just like the example that I talked about at the very beginning. If I'm trying to predict your first year college GPA, instead of just using your high school GPA or instead of just using your SAT, I could put both of them together and come up with a plain equation in order to predict your first year GPA. Okay? So those are things that you can easily do in R, and it's very, even though I may not write down all the formulas, you can understand what you're doing is minimizing the sum of the deviation square. Okay? And that's it for today. Okay? So thanks a lot. And I'm at the Learning Center today. So if you want to come by to ask questions on any of the stuff on your homework, feel free to come by.